मैंने कर दी सर, रिकॉर्डिंग अनपॉज कर दी, रिकॉर्डिंग चालू है। ठीक है,
रिकॉर्डिंग ऑन कर दिया आपने?
ऑन कर दिया, चालू है रिकॉर्डिंग अभी।
अच्छा
आपको
अच्छा,
लगता है तो आप उसको पॉज कर दो, मैं भी होस्ट बना रहा आपको।
हाँ होस्ट बना दीजिए।
ओके।
Okay, so we are starting with MOSFET. So the small signal analysis of, we are on a small signal analysis of small signal analysis of MOSFET. Small signal analysis of MOSFET. है ना? Let's see how this works. Let's see how this works. So I can say, let's take common source configuration. So what I can say in common source configuration, we are having one drain resistance, and this is connected to ground. And we have the supply, which is capital V, and let's say this is small v. So what I can say, there are two types of supply here, AC and DC. So current in the MOSFET, it's the same approach as we discussed in our analysis of as we discussed in our analysis of bipolar junction transistor. It's the same approach. So what I can say, I am interested in AC analysis of this, and for AC analysis of this, what we can say, assume all DC quantities equal to 0. So let's say all DC values are equivalent to 0, or DC values are equivalent to 0 in this discussion. So we can say all DC values are equivalent to 0. So let's say I of D represents AC summation of AC and DC value, which is known as instantaneous value. And what I can say, ID is summation of small id plus capital ID. So this is summation of two things. Instantaneous value, this represents the small signal component. Why we are saying small signal component? Because we want AC, we want a linear amplification. A small signal and this represents DC component. So what I can say, the voltage will be the transistor will work as a amplifier only in flat region, the flat characteristics of the this is, let's say, IDS and this is VDS, or I should say this is IDS and this part represents this is the point where I can say the value of VDS is equivalent to VGS minus of VTH, and this is the characteristics. This is the characteristics of transistor, and this region, this is known as saturation region. In saturation region, transistor acts as an amplifier. So we know that what is the current in saturation region? The current in saturation region are IDS equal to some mu n 1 by 2 mu n into COX into W by L into VGS minus VTH whole square. This is the current. So we want a separation between AC and DC quantities. We want a separation between AC and DC quantities. So how to do this? I can say IDS is equivalent to, let's say this is K. This is some device parameters. I am taking this as a K into VGS minus of VTH whole square. But this relationship is non-linear relationship. We want to bring it into the linear region. So what I can say, IDS an instantaneous value. IDS is equivalent to K times of VGS plus VGS minus VTH whole square. This is the idea. And now what I can say, I of ds can be written as K times of VGS minus VTH whole square plus VGS whole square plus 2 times of VGS into VGS minus of VTH. Okay. So I can say this can be written as capital of IDS plus small of IDS equal to K times of VGS minus of VTH whole square plus K times of VGS square plus 2 times of VGS into VGS minus of VTH. This is total idea. Now what we can say? That IDS is DC current, and DC current is this K times of VGS minus of VTH whole square, and small part is IDS equal to K times of VGS whole square plus 2 times of VGS into VGS minus of VTH. And can I say this part is a non-linear part? This is non-linear part. So how to take this, and this is non-linear part, and we want to design one linear amplifier. So how to make this part minimum is only if VGS is very small signal in millivolts, microvolts. है ना, VGS का वैल्यू अगर बहुत ज्यादा स्मॉल होगा तो यू कैन से VGS very small, then you can have the non-linear part. Means what condition is required? We can say the condition required here is we want VGS square should be less than 2 times of VGS minus VTH. Now we can cancel this. So if this is the condition, if this amplifier satisfies this condition, then what I can say? I can say that this may work in the linear region, but yes, there will be a second harmonic distortion because of you are neglecting VGS square. This is the idea. Now what I can say? Let's say this condition is true, then I can say that a small IDS equal to K times of VGS into VGS minus of VTH. Correct? Or we can say del IDS equal to K times of del VGS into VGS. We are talking about a differential resistance, differential transconductance, and we know that IDS is output current and VGS is input voltage. So I can say the ratio of del IDS divided by del VGS is known as GM, and GM is what? Transconductance, and this ratio is equivalent to K times of under root of VGS minus VTH, which also known as overdrive voltage, DC overdrive voltage. So this is the idea. So I can say ID equal to GM equal to K. What is K? And we have left one term which is 2. This is 2. Here I can write 2. So this is 2 times of K. K is what? 1 by 2 mu n into COX into W by L into VGS minus of VTH. Correct? Or I can say this 2 are cancelled. So can I say GM equal to mu n into COX into W by L into VGS minus VTH can be written as IDS, capital IDS, we can say, we want to write this part. So can I say this part is VGS minus VTH? So I can say VGS minus VTH whole square into is equivalent to IDS divided by 1 by 2 mu n into COX into W by L under root of this will make sense. So I can write here, I can say this is IDS divided by 1 by 2 mu n into COX into W by L. So GM can be written as the transconductance of MOSFET can be written as it's a 2 because we have 2 in this side mu n into COX into W by L into IDS. So this can be expression of transconductance. Only one term is required, which is okay. Now what I can say, this is also we can say the MOSFET can be MOSFET can be written as in saturation. You can say MOSFET can be written like this. This is IDS as a function of VGS. So, or what I can say, let's draw the small signal model for to write it better, I can write output voltage VDS can be seen as a function of IDS. So this is the idea for the circuit. So let's see what is the small signal model for common source. A small signal model. So first we are having one transistor. So common source arrangement, we are going for the common source. This is VD, this is RD, and source is connected to ground. Let's say source is connected to ground, and for AC, let's say this is V of S, and we are taking output from here. Like BJT, वहाँ collector से लेते थे. Now we are taking output from with respect to ground, VDS. So let's draw this first. Bipolar junction transistor पढ़ते time, what we had discussed that the base emitter junction is forward bias. There is no such thing here. So you can say here we can draw a gate junction, a gate terminal. We are drawing the small signal equivalent. Then we are having one source terminal. So you can say this is VS. Now this potential is known as VGS. This terminal is known as gate terminal. This terminal is known as source terminal, and current here is GM into VGS, and this potential, this terminal is drain terminal, and we can take output from here between VDS. So this is the fundamental arrangement. How fundamental arrangement looks like? The fundamental arrangement looks like this. Fundamental arrangement looks like this, and you can add the remaining components here, but this is basic model, basic small signal model. Basic small signal model. This is basic small signal model. So for what I can say for our common source circuit, common source circuit, for common source circuit, what I can say that we are having Vs. So let's start with this. Let's draw this again. This is our okay. This is our source terminal. This is connected to ground. This is आपका अंकल पूछ रहे थे कोयल आंटी आगे क्यों नहीं आई? नहीं सुन गए क्या? This is V of S. This is plus minus VGS. Then we are having this is dependent source, but okay, I am making it round, so you can say this is dependent source. Okay, can I say this is GM into VGS? This is RB, because a resistance is connected between, this is our gate terminal, this is source terminal, and input resistance is the infinite, makes life easier because there is isolation between gate and remaining body. And what you can say, you can take output from here. That is VDS. So this is the whole idea for the small signal model. Now what I can say, let's find the current gain of this, voltage gain of this amplifier. Voltage gain is ratio of VDS divided by Vs. So I can say this is known as voltage gain of the common source amplifier, and VDS is given by minus times of Gm into VGS into RD. And from here we know that Vs is equivalent to VGS. So I can say VDS is equivalent to minus Gm into Vs into RD, or you can say the voltage gain of this circuit is minus Gm into RD. And this is one ideal model. What you can say, this is one ideal model. Yeah? It's because this resistance is not infinite. It's too high, but not infinite. But too high resistance will make most of voltage Vs drops across VGS. So this is the idea. Now we are interested in output resistance. So how to calculate output resistance? The resistance from this point. Resistance. This resistance is known as output resistance, R out, and we are interested in this resistance by making VGS equal to 0. So if VGS equal to 0, you can say this current source will act as an open circuit. So you can say the R out for this circuit is equivalent to RD. R out का वैल्यू किसके इक्वल होगा? RD के इक्वल होगा. R out is equivalent to RD ohm. Correct? Now we are interested in input resistance. Suppose you are having one resistance here RS, so we don't care about this. This resistance is known as Ri, and Ri is equivalent to infinite, which makes it suitable for the voltage amplification purpose. Now there is no loading, at least in this case there is no loading effect. Vs is equivalent to VGS in the circuit. So this is the whole idea for the circuit, and we can calculate all the parameters by using this circuit. Let's take a few more examples based on this small signal analysis. So in a small signal case, we want to analyze all the cases जो कि हमने कहाँ देखे थे, जो cases हमने देखे थे in analysis of जो cases हमने सारे देखे थे किसके analysis में, जो cases हमने देखे थे bipolar junction transistor के analysis में, those cases we want to analyze here. So what I can say there are three basic arrangements, three basic configuration for small signals. Three basic configuration known as common source, common drain and common gate. जैसा बाइपोलर जंक्शन ट्रांजिस्टर में हमने देखा था कि कॉमन सोर्स इज हैविंग लो इनपुट रेजिस्टेंस, तो फिर आपने क्या किया था कि यू हैड वन रेजिस्टेंस एट सोर्स टर्मिनल, फिर इनपुट रेजिस्टेंस उसका इंक्रीज हो गया, फिर आपने देखा सेकंड कॉन्फ़िगरेशन इज कॉमन बेस, और कॉमन बेस कॉन्फ़िगरेशन में आपने क्या देखा कि इन कॉमन बेस कॉन्फ़िगरेशन यू आर हैविंग a good frequency response but no current gain. In common collector में you have the highest current gain. So this is the idea, है ना? The three basic configuration is common source, common drain and common gate. So let's say what is common source. I am only drawing the AC analysis part. So what I can say, common source you can draw like this. This is Vs, okay. Then we are having V output. This is your drain RB, or you can take RL, and one we are having a source resistance. This is connected to ground. So you can say this arrangement when you have input at gate terminal and output at drain terminal. This is common source, जैसा कि अभी हमने देखा. Common source arrangement. Next arrangement we are having is known as common. Next arrangement we are having is common gate arrangement. So what I can say, this is same as okay. This is common gate. So I can say gate is connected to ground and this is source. So we will apply a voltage at source terminal. a voltage at source terminal Vs, and you can say this is okay. This is RD and this is V out. So this configuration is known as common gate configuration. Gate is common. You are supplying, you are connecting source at source terminal and taking output from the drain terminal. So this arrangement is known as common gate arrangement. Next arrangement we have in the small signal analysis is common drain arrangement. So can I say common drain arrangement, the third arrangement. So drain is grounded, so I can say supply is connected to source terminal, then we are having one drain terminal which is connected to 0, and we are taking output from source terminal. We are taking output from here. This is RL and we are taking output from here. जैसा कि आप बोलते थे उसको emitter follower in BJT, this circuit is known as source follower. Source follower, or also known as common drain circuit. This circuit is known as source follower, or also known as common drain circuit. So this is the idea for all the circuits, and again besides amplification, all the properties are important which are input resistance, output resistance and all. So let's start with the, okay, like we had a RE model in bipolar junction transistor, the same we are having RE model or T model here. One more model, one model is what? Hybrid model, which we had discussed. Hybrid pi model. And what I can say, hybrid pi model looks like this. This is our gate terminal. Then we are having one source terminal, then we are having one GM into VGS. This is source terminal, this is drain terminal, and this is gate terminal. Likewise, this model is known as hybrid pi model. One more model we are having for this discussion is known as T model. So you can say first terminal is gate terminal. You can say this is gate terminal. And the gate terminal is having zero current. Then what we can say, we are having one more terminal. This current is IDS, and we are having one resistance which is 1 divided by GM. So this is our drain terminal, this is our gate terminal, and this is our source terminal. So these are three terminals. These are three terminals which हमने वहाँ भी सीखा था कि if there is an resistance at source collector terminal, you can use RE model or T model, otherwise you can use any model, है ना? So ऐसा कोई specific rule नहीं है, but when to reduce the calculation, whenever you are having one resistance at source terminal, you can go for this model. So कोई परेशानी नहीं है using this model. So let's start, and what I can say, we are having one circuit in which common source with source resistance. I am using one more additional resistance, which is source resistance. So let's draw the small signal model for common source with source resistance. Common source with common source with source resistance. So So let's take one example with common source with source resistance. जैसा कि हमने वहाँ देखा था common emitter with emitter resistance. This is small signal configuration where we are having common source with source resistance. So you can say this is my input sensor signal voltage Vs, and this is source resistance Rs, which is of course unavoidable. Then we are having one drain resistance RD, and then we are having a source resistance Rs. And now I am interested in the small signal analysis of this. So in this we can use our T model. We can use our T model to analyze the circuit. What I can say, we can use T model. T model to analyze the circuit. So what I can say, first terminal is gate terminal. So let's draw one gate for analysis of this. Let's take one gate terminal, and a resistance is connected to this is Rs, and then you are having which is V of S. Then what I can say, a current source is connected, a current source IDS is connected here. Then we can say this is our drain terminal. Between drain and ground there is one resistance which is known as RD. This is V out, and this is known as 1 by Gm. This potential is known as VGS, and this is your source terminal. So between source and ground there is resistance Rs. So this is resistance Rs. So this is complete idea for the circuit. So this is the complete idea for the circuit. What we say, this circuit is a common source with source resistance. Now let's calculate all the parameters. What is gain of this circuit? What I can say, let's calculate gain of this circuit. What is gain of this circuit? Gain, voltage gain. So can I say the output voltage of this circuit is nothing but minus ID into RD, because we are having current in this direction. So original direction is this, so I can say VO equal to minus ID into RD. This is the value of what is value of ID? So you can say this current go through here. So you can say if this current is equivalent to 0 because gate is isolated to the device, this current is 0 means the potential at this point is Vs. So can I say the current ID is having value Vs, which is this value, minus Vs minus 0 divided by 1 by Gm plus Rs. So this is the value of ID here. This is the value of ID here. So can I say ID can be written as Gm into Vs divided by 1 plus Gm into Rs, or you can say the output voltage of this device, of this configuration, is equivalent to minus of Gm into Vs divided by 1 plus Gm into Rs multiplied by Rd. So you can say V out divided by Vs is equivalent to minus Gm into Rd 1 plus Gm into Rs. So because of the negative feedback this Rs provides, the gain will be less, and what you can say, the gain will be Gm into Rd divided by, without Rs this is the gain. If you take Rs equal to 0, gain is minus Gm into Rd. So this is the relationship. Now we are interested in input resistance of this. Input resistance is infinite because apply voltage and current. What is input resistance? You can say the input resistance is this, but what you can say, this is Ri. So applied voltage is Vs, and this Vs is drawing 0 current. So you can say Ri is equivalent to infinite. And what is value of Rd? What I can say, the value of Rd is equivalent to this R out. R out by making VGS equal to 0. So if VGS is equivalent to 0, you can say this current is equivalent to 0. So R out is equivalent to Rd. So these are a lot of parameters. Output resistance is good. Input resistance is very good, good for voltage amplification, but current gain is less. So this is our analysis for common source with source resistance. How we can analyze? This is way to analyze the circuit. Now we are having next circuit, which is common gate amplifier. So let's start with the common gate. Maybe amplifier or not amplifier, let's see. But yes, small signal analysis of common gate configuration. First we will find all parameters, then we will compare. A small signal analysis of common gate. So what I can say, this is connected to ground. This is my source terminal. This is R signal. This is V signal. Then we are having one output RD. This is V out. So again we are having one resistance at source terminal. So I will use our T model to analyze the circuit. I will use T model to analyze the circuit. Okay. So what I can say, how to use this in to analyze the circuit. So I can say we are having one gate terminal. This is our gate terminal which is connected to ground. Which is connected to ground. We are having one this is I. This is RD. This is V out. Then we are having one by GM. This current is 0, so no problem in this. Then we are having one R signal. And we are having one V signal. this is the total circuit which we want to analyze. So let's see how this circuit will work. Okay. So let's calculate the input resistance of this circuit. Input resistance of this circuit. So I can say by removing the supply, this resistance is known as input resistance. So you can say if you remove the supply, the input resistance is this resistance is 1 by Gm. You can calculate by any technique. Let's apply a voltage source here, and voltage source means V test minus 0 divided by I test. So you can get V test by I test ratio is equivalent to 1 by Gm. So this is input resistance. Now we are interested in output resistance of this circuit. So you can say the output resistance of this circuit is equivalent to R out by making input is equivalent to 0. So okay, this resistance is equivalent to RD. This is output resistance. Now I am interested in voltage gain of this amplifier. Voltage gain of this amplifier. So can I say V out is equivalent to minus of I times of IDS times of RD, and this current is 0, so same RD IDS current flow from here. So you can say VGS divided by, we can have the relationship V signal means this voltage divided by R signal plus 1 by Gm is the value of minus IDS. This is the value of minus of IDS, because we are taking current higher potential minus lower potential. So I am considering current in this direction, but the actual current IDS is having opposite direction what we have assumed. So what I can say, V out is equivalent to minus IB into RD, or you can say this is minus and minus plus, so this is V signal R signal plus 1 by Gm multiplied by RD. So what we can say? The out is GM into RD divided by 1 plus R signal into GM. So this is the voltage gain, and we don't have 180-degree phase shift of input and output. There is no 180-degree phase shift between input and output. So what I can say, because of low input resistance, what I can say, this common gate is having application, common gate, because of low input resistance this is useful for amplification of frequency response of common gate is better than remaining two. So amplification of high frequency signal coming from low resistance. Coming from low resistance source. That includes cables, transmission lines, like transmission line. So what we can say, the transmission line is having, this can act as a load for transmission line. But this is your common gate array circuit. So low resistance and frequency is high. You can have 50 ohm transmission line or 60 ohm transmission line like this. So this is the idea of now the next circuit we want to analyze is common drain circuit. So let's start with the source follower or common drain circuit. The next circuit we want to analyze is common drain circuit. The next circuit we want to analyze is common drain circuit. So what I can say in common drain circuit, this is R signal, this is we are having V signal this is R signal, this is our gate terminal, now we are having drain is connected to ground, this is our source terminal, and we are taking output from this terminal. And again, what I can say, this is my load and this is my Vout. So again, we are having one resistance at the which terminal? We are having one resistance at source terminal. So we will go for RE model. So let's start. This is R signal, this is V signal, then this is I, this is 1 by GM, and this is connected to ground. This terminal is connected to ground, and we are having one more resistance, which is RL. This is whole arrangement. So again, we are interested in the output resistance of this circuit. So can I say what is input resistance? So you can say there is no connection between, because this current is always equivalent to 0 if it's a threshold, but current will be very less. So this is 0. So we can say the value of Ri for the circuit is equivalent to infinite. What is the value of output resistance? So you can say by removing the load, you can say this is output resistance, and output resistance is what? 1 by GM. By making source equal to 0, you can say this is 0, so 1 by GM. So what you can say, R out for the circuit is equivalent to 1 by GM. The output resistance is equivalent to 1 by GM. And what is output voltage? So can I say this current here is I. So we can say V out equal to I into RL. And what is value of I? So you can say this is V signal. So I is equivalent to V signal divided by 1 by GM plus RL. This is the value of current. So I can say V out is equivalent to GM into RL GM into RL, and this is 1 plus GM into RL divided by 1 plus GM into RL divided by V signal. So you can say this is approximately 1. So voltage gain of this amplifier is equivalent to 1. So this is idea for the circuit. That's why this circuit is known as voltage follower or source follower. This circuit is also known as source follower circuit. From tomorrow we will start the cascode amplifier, which is a better, which you can use in IC technology instead of using this biasing resistance RD. You can use a current source. So that is cascode amplifier. So we will talk about cascode amplifier in tomorrow's class.